Hi everyone, welcome back. In this video, I will go over inorganic nomenclature and practice some examples. And so this information was published in an article back in 1992 in Journal of Chemical Education, but it gives a really nice summary of all the rules. And it's really important as a chemist or any scientist that you become familiar with the vocabulary in the field. And so when you're working word problems and you're given these names, you need to be able to translate what that name means into a chemical formula so you can predict the correct chemical reaction and balance it correctly. So we're going to start off looking at the positive ions. Positive ions are referred to as cations, and they can be divided into monoatomic or polyatomic cations. Now, there are cations that form only one common ion, and so these are, for example, like sodium +1 always forms a +1 charge. And when we name the element, we always use the full name. And so if we're looking at sodium +1 on its own, we refer to it as the sodium ion. Same goes for magnesium and hydrogen. Now, just make a note here that the number of positive charges is not indicated in the name because it's just not necessary. Once you learn the correct charge that it wants to form in nature, it doesn't change that. So there are cations that form more than one common ion, and these fall in the transition metals, that block D, as you would say on the periodic table. Now this is the newer rule, and the rule that you would use in my classroom and in any chemistry classroom at this day and age. Basically, we name the element with positive charges and we indicate their charge using a Roman numeral. So for example, here you see iron 2 plus cation, and so the way it's written is iron parentheses 2 Roman numeral 2 ion. And that's because iron forms iron 2 in nature, but also iron 3, and we need to be able to distinguish between the two. Now, some of you may be familiar with the older rule where you have the Latin stem for the element plus OUS or ic. OUS for the lesser charge, ic for the greater charge. So for example, Fe2 plus is ferrous, and then Fe3 plus is ferric. Like I said, that's less common in this day and age, but if you do see that in older literature, then that OUS and ic stand for the charge for that particular cation. And there's also some special cases, the polyatomic ions, and these you'll need to learn. So for example, ammonium is the name of NH4+. Hydronium is the name for H3O+, and these are very commonly used in general chemistry. There's also the mercury plus mercury 1 ion, and it doesn't exist as a monoatomic ion, and they're actually two Hd plus ions bonded together. Okay. Now there are also the negative ions referred to as anions. When you name these if you're referring to the monoatomic anions, we use the stem of the element plus IDE. So for example, if you have H and then a -1, that is hydride. Okay. Fluorine would turn into fluoride, oxygen turns into oxide, nitrogen turns into nitride, and carbon turns into carbide. Now if you have oxyanions containing oxygen, then if you have the least oxygen, then that turns into hypo, and then the stem of the name ite. So for example, hypochlorite. If you have less oxygen, then it's the ite ion. So for example, the chlorite ion. If you have more oxygen, turns into 8. So CO3 minus is chlorate. And if you have the most oxygen, it turns into per, stem name 8. And so this is perchlorate for ClO4 minus. And so the chlorine series has 4 of these ions, and so it goes from the hypoite, the ite, the ate, and then the perate. But for example, the sulfur series doesn't have 4 species, it only has 2. And so when that happens, when only 2 of the 4 ions exist, then you only use the ite or the ate. So you can see here SO3 2 minus is ite, SO4 2 minus is ate. Now there are exceptions and other polyatomic ions, for example, that you'll need to learn. And so, for example, hydroxide, very common, OH minus, cyanide, CN minus, thiocyanate, looks like cyanide but has a sulfur in it. Thio represents sulfur. Cyanate has the oxygen. Peroxide is O2 2 minus, as in like hydrogen peroxide, for example. O2 minus is a superoxide ion. C2H3O2 minus is acetate. That's the conjugate base of acetic acid, which we will commonly use in my course. Dichromate, Cr2O72 minus. Oxalate, C2O42 minus. Manganate, which is MnO42 minus. And then permanganate, which is MnO4 minus. All right, so there are oxyanions that contain hydrogen, and so we usually have hydrogen plus the oxyanion, and so the way you would name that is hydrogen, name of oxyanion, or sometimes referred to as bi plus the name of the oxyanion. So the one you may be most familiar with is HCO3 minus, so that's the oxy anion with hydrogen, and it's referred to as hydrogen carbonate, but you may be more familiar with bicarbonate, which is the key component in baking soda. All right, and you can see here, HSO4 minus is hydrogen sulfate. Look, you see the SO4 minus, that's the name of the oxyanion, sulfate. It could also be called bisulfate. Here we have hydrogen phosphate. Phosphate is PO4. 3 minus is just that anion alone. Now, if you have 2 hydrogens, then we call that dihydrogen, name of oxyanion. So for this guy here, it'd be dihydrogen phosphate ion. Now, I just wanted to make note that the rule applies to ions only. So you can see ions are anything that has an overall charge. For example, H2CO3 is called carbonic acid. It doesn't follow these rules, and it's because it's a compound, not an ion. All right, so let's glue this together. Let's make some compounds. Now, starting with ionic, traditional cation and anion, you name the full cation as we discussed in the previous page, and then you name the anion depending on if it ends in IDE or if it is the name of a polyatomic ion. So for example, here, full name sodium and then chloride, magnesium chloride. Here, the cation, because it's a transition metal, we had to indicate its charge. This is iron 2, and then nitrogen turns into nitride. In this example here, we have sodium, full name, and then CO3, 2 minus, is a polyatomic ion. Its name is carbonate, so you don't change the name. You just use the name as written. Here we have ammonium hydroxide, the 2 polyatomic ions. Here is sodium hydride. This is a hydrogen with a -1 formal charge. And then calcium hydride. Now, something to make note here is that the name does not indicate the number of cations or anions, because there's only one possible way for those ions to combine to form a neutral compound. So when we are creating ionic compounds, the overall charge is 0. So there's no need to add prefixes to ionic compounds. There's only one possible way to combine the cation and the anion together to make a neutral ionic compound. Now, compounds that contain hydrogen. So, hydrogen in a nonmetal. In the absence of water, we name these species hydrogen stem name ide. So, for example, if we had HCl, but it wasn't in water, which we would call that anhydrous, this would be hydrogen chloride. HF, hydrogen fluoride. H2S, hydrogen sulfide. So basically, these hydrogen-containing compounds are named as if they were ionic compounds. Okay? However, when we purchase a lot of these types of materials, they're usually dissolved in water. And therefore, the name changes to hydroic acid. And so therefore, as you see here, HClAq stands for aqueous, means it's dissolved in water. It's hydrochloric acid. HF turns into hydrofluoric acid. H2S stands for hydrosulfuric acid. And the AQ in the formulas of the acids, once again, sometimes is omitted because usually it's clear in the context that they are acids. So when you purchase for example, when I purchase hydrochloric acid from a chemical company, the most concentrated form is 12 molar. And basically that's as much of the hydrogen chloride they could bubble in solution. We've reached maximum solubility, and we'll discuss that later in future videos. When we purchase it, once again, it always comes in aqueous solution. Okay? And different types of gases can dissolve in different concentrations, just depending on their solubility in water. All right, so moving on. Hydrogen, if we have a hydrogen and an oxyanion, let's say we have absence of water here in the first part, we name them like ionic compounds. So hydrogen hypoite, hydrogenite, hydrogenate, hydrogen perate. And so we've talked about naming these oxyanions on the previous page just alone, but if they contain hydrogen, we put hydrogen in front of there. Right? So for example, like hydrogen hypochlorite, hydrogen chlorite, hydrogen chlorate, or hydrogen perchlorate. However, if they're dissolved in water, then that changes from hypoite to hypous, acid, ic acid, peric acid. So for example, we have hypochlorous acid, chlorous acid, chloric acid, perchloric acid. Now remember that some species only contain two. So the nitrogen series is nitrite, nitrate for the anion alone. And so therefore that turns into nitrous and nitric. We also have the sulfur series, sulfurous, and then sulfuric. And then you have phosphoric acid. Last but not least, covalent compounds are when we have a nonmetal bonded to a nonmetal, and that's where electrons are shared. Generally, the less electronegative element is first when writing it. Exception is when one of the elements is hydrogen, and I'll talk about that at the very end of this page. The number of atoms needs to be specified by a prefix, because with covalent compounds, there's more than one way to combine, for example, carbon and oxygen together. In addition, the prefix mono, if it's at the beginning, it's usually dropped. So for example, carbon monoxide. We don't normally say monocarbon monoxide. We drop the mono in front of carbon and just say carbon monoxide. Make sure that you become familiar with these prefixes if you're not already. So as you can see here, carbon monoxide, right, so on and so forth. Now, if you do have a prefix, more than one for that first element, we do need to include that prefix. So dinitrogen monoxide, we're not going to drop the di in front of nitrogen, and we need to know that there's actually two nitrogens as opposed to one. Now, just a general comment, tetraoxide becomes tetroxide, monooxide becomes monoxide, so the name just sounds better. And as I was stating earlier, hydrogen-containing compounds do not necessarily follow the rule when it concerning the order in terms of putting the less electronegative atom in the front. And so these types of molecules should just kind of be memorized here. So for example, ammonia. You'll see that quite a bit in general chemistry. It's not written as H3N, it's written as NH3. However, a lot of times, when learning inorganic nomenclature, there's a lot of rules, obviously, as we just went over here. But think of it as learning a new language. And so when you learn a new language, you have to always continuing practice speaking that language fluently to the best of your ability. You can't just stop, then you're going to forget, a lot of your vocabulary. And so think of chemistry in the same way. That these names are a way that we communicate with one another in terms of, what kind of chemicals we have in our beaker, for example. So just continue to practice this. Review over these rules as I have just reviewed over them with you, and practice problems and continue to practice them so that becomes second nature. All right, so let's just practice some problems together so I can teach you some tricks on how to approach naming inorganic compounds. So these problems are asking us to form an ionic compound with the following elements and polyatomic ions. We'll also need to name the compound's form as well. So, for example here, we have ammonium, and so I like to write down the ions on their own. So ammonium is NH4+. Phosphate is PO4 3-. Now, a trick to writing the correct formula is to do the crisscross rule. And so, for example, you can put the 3 down here, so it goes crisscross here. So 3 down here, and then for the phosphate, just 1 down there. Make sure when you're working with polyatomic ions that you put parentheses if there's more than one polyatomic ion. This is basically one group here, and we need to say that there are 3 total ammonium. It would be incorrect if you wrote something like this. I'm just going to write it on the side. And as you can see here, this just does not look correct at all because it appears that there's 43 hydrogens when in this case there are not. And so be mindful with polyatomic ions to show the parentheses if there's more than one polyatomic ion. You notice I didn't need to put parentheses around phosphate because there was only one phosphate. Now, if you wanted to check your work mathematically, you could do an algebra expression. Remember, ionic compounds always should add up to 0. And so, for example, here we said that there are 3 ammonium. Each ammonium cation is a +1 charge. And there is 1 phosphate, and each phosphate is -3. And this does indeed add up to 0, right? And so this here are the number of atoms on the outside, and in the inside of the parentheses I put the charge to make sure it adds up to 0. So like I said, you can do that as a way to double check your work. All right, we also need to write the name. So the nice thing about polyatomic ions is you just keep the name as is. So for example here, this is ammonium. We don't change the names at all. So it's ammonium phosphate. Do not be tempted to change the ending of this name as a polyatomic ion. There is definitely a difference between phosphate and phosphide. So be very careful with that. So with polyatomic ions, do not change the name, just include the name as written. All right, let's do the next example. And if you want to pause right here and try to do the rest on your own, that would be fantastic. It's great practice. And then check your work with me. Always when we do any kind of practice problems, that's a great strategy to make sure you know for sure you've mastered the material. And if you haven't, then you know which areas you need to brush up on, okay? All right, so let's go ahead and do the next part. We have aluminum and sulfur. And what may be really helpful here is having a periodic table handy. All right, and so I'm going to find aluminum here. Now, aluminum is in group 3A, which means it has what charge? It has a 3+ charge. Fantastic. And we also have sulfur, which is in group 6A, which means it has a what type of charge? It has a 2 negative, right? Fantastic. And if we did the crisscross rule, how many aluminums would we have? We would have 2, good. And sulfur? 3, excellent, right? So Al2S3. Now be mindful that your, one second here, that you do not, when you do the crisscross rule, do not carry the charges down. Sometimes I'll see students write Al -2, but these are the number of atoms, and you can never have a negative number of atoms. So don't fall into that trap. Always ask yourself, does this make sense? So make sure when you do the crisscross rule, you only bring the number down, not the charge. All right, so what would be the name for this compound? Good, so full name for the cation, aluminum, and then sulfur turns into sulfide. Fantastic. Good. All right. So if we look at cobalt, I'll bring up the notes again. All right. So if we look at cobalt, cobalt has a what kind of charge? Excellent. It is 2+. Fantastic. And hydroxide is a polyatomic ion. What's its formula? -1. Good. OH -1. Crisscross rule. How many cobalts do I have? Just 1. How many hydroxides do I have? 2. Excellent. And what would the name be? Cobalt 2. Always include the Roman numeral for those transition metals because they change their mind. Hydroxide, excellent. Keep the name of the polyatomic as is. All right, if you have your periodic table handy, what is the charge for magnesium? Always 2+, good. And nitrate is a polyatomic ion. NO3-, excellent. Crisscross rule, how many magnesiums do we have? 1. And nitrates, we have 2, right? And therefore, what would the full name be? Magnesium nitrate. You do not need to include a Roman numeral because magnesium never changes its charge. It's always a +2 cation. All right, and then finally, we have iron 3+. And oxygen, like sulfur, is in group 6A, so it has a -2 charge as an anion. And when we do the crisscross rule, it'd be Fe, and then how many? 2, good. O3, excellent. And therefore the name would be iron 3 Oxide. Excellent. Good. Fantastic. So make sure you practice those. Practice other problems besides these problems to make sure you feel confident in your inorganic nomenclature. Just one final note though, a lot of times students will fall into the trap of writing, for example, iron 2 oxide. Remember that the Roman numeral indicates charge, not the number of atoms. One final note before we wrap up here is to remember that in nature there are diatomic molecules. So for example, you may hear or do a word problem and it says, in the combustion reaction, propane gas reacts with oxygen gas. And so it's important that you recognize that oxygen in nature is not monoatomic, but rather diatomic. And why it's critical that you know that is if you were to write the combustion reaction and you did not use the subscript 2 here, that would mess up balancing the entire equation, right? And therefore you would get the wrong answer. So just make sure that you review over the 7 diatomic molecules in nature, and those are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. All right, well that wraps up our discussion of inorganic nomenclature. Thank you for watching and see you next time.